Hey guys, I am getting there. I'm sorry, I got distracted with Ginger. So let me just finish, and I just sent the reminder out. That's good. That's good. That's good. We don't need this. Let me do a share screen. Share screen, Epic Pen, and open this up, and then we're ready to go. Hello, welcome, welcome, welcome. Tonight is going to be so cake. We're going to probably have this done in like a half hour, 40 minutes tops. It's one of our, yep, I remember your name, Sammy. It's one of our quick topics. So if I had you in school, you already got this piece of paper. If not, I did send it to your parents, and I think I gave you the link in Google Classroom. There's only 12 multiple choice questions. So worst case scenario, follow along on the screen. And then you can just write it down in your book when I give you the papers tomorrow. As a reminder, tomorrow we are doing our big day from 2:30 to about 4:45. I am ordering pizza. I think I'm going to end up getting 10 pizzas. So hopefully a lot of people come. Jada, Camille, yay. So that's what's happening tomorrow. And then we're also going to do one tomorrow night at 7:00. Tuesday, there is nothing after school, but we are going to be doing something on Tuesday night. We're going to go over the same kind of stuff. So today is probability. We did spend, believe it or not, like 5 or 6 days doing probability. You might not remember many of them because we did them before spring break. On the review sheet, this is kind of what you need to know. These are the 3 main things. Let me put my glasses on. These are our 3 main things that we care about on the review sheet when it comes to probability. According to the EOC, 15% of the questions are on probability. Figuring there's about 73 questions. You're looking at an average of like 9 to 10 questions on probability. So we've got conditional probability, the multiplication rule, and the addition rule. Basically, the multiplication rule is when it happens in both places. Hey, Brea. And addition rule is when we use or, but we're going to see some examples coming up right here. Okay, so unit 7 probability. Yay! You probably were like so excited to write this unit down because it was so short compared to some of the other units I made you all write down. So let's be realistic on that. Probability is the likelihood of an event occurring. Experimental probability, that's when we talked about where do you like to eat chicken? Do you like going to Zaxby's? Do you like going to Chick-fil-A? That's experimental probability. We collected data from the classroom, and that actually is what happened. Theoretical probability is what happens. It's supposed to happen. Complement is the probability of something not happening. So like today, the probability of it not raining was, 100% because it didn't rain. Again, this is all you wrote down in your book. Simple probability is a probability of a single event occurring. So the probability of picking one red gummy bear, but not putting it back, not getting a second red gummy bear, just like one red gummy bear happened. Compound probability is the probability of multiple events occurring. So you pick a red gummy bear. Do you eat it? Do you put the gummy bear back? What do you do? That's the second one. Independent events is 2 events which the outcome of the first event does not affect the outcome of the second. So, for example, I pick a card and I put it back. Independent, because I put it back, it's fine. But dependent is I had my card and I'm holding my card in my hand. So if you remember that card activity that I made a quiz grade where it was like, here's a 3. What's the probability of getting higher? What's the probability of getting lower? What's the probability of getting 11? Those were all dependent because after you flip the card was gone forever. After you flip the card was gone forever. So that was that whole premise there. Then we did Venn diagrams, and I really liked this picture a lot because it kind of like helps us to visualize all those vocabulary things I just talked to you about. Complement, where we're looking right here. Again, is that not happening? So if it happens in the circle, it can't be outside the circle. You're either in the circle or you're not in the circle. Mutually exclusive. They also use this word independent for mutually exclusive. Again, here's an example of something that's mutually exclusive. riding a bicycle and going to the movies. Riding a bicycle has nothing to do with going to the movies. Okay. Mutually exclusive. So if something is independent, one does not have any possibility of the other. Okay. It doesn't cause the other to happen. Union is when there's an overlap. Okay. And basically, when you do union, it means all. And think about this. When two people get married, they bring all their stuff together. Now, technically speaking, we know a lot of stuff's going in the trash or going to Goodwill or going to Salvation Army because you can imagine two whole households going into one. But in essence, union means all the stuff comes. Everything comes. Intersection is just this little weeny, teeny weeny place. Think of it like streets. You have one street going this way, one street going this way. The intersection is just where like my elbows met. That's it. The intersection is the overlap. Okay. Intersection is overlap. Union is all. Okay. If something is independent, I know I use the word up here, but if something's independent, basically all you're going to do is multiply those probabilities together. And that's where you're going to get the and statement. Let's look at intersection a little bit more. The intersection of, I'm sorry, Prince, were you talking to me, honey? The intersection of the probability of A and the probability of B means that the probability of both A and B occurring is denoted by that symbol, which we've talked about before. Okay, that should not be new because you wrote it down in theory. If the outcome has no impact upon the outcome, then it's said to be independent. So no impact means independent, and we just do our plain old multiplication thing. However, if it is dependent, then it gets to be this longer thing, which is the probability of B given A. And here's an example. The probability of drawing a red card, then drawing another card, given that the first card was red. So for example, if you don't get a red card on the first try, we don't even continue the problem. But you're going to continue the problem because you're always going to assume the first thing happens. So whenever you get a given, that's when we get involved with this formula, and this formula is on the formula sheet, so you don't have to worry about it. But whenever you get given, this is where it comes into play. The probability of drawing a red, given that the red card was already drawn. Okay, here's union again, talking what we talked about before. The union means the probability of A or B. It's all the stuff. It's either in his house or it's in her house. They bring it together, or his and his and hers and hers. I don't care. But basically, everything comes together. If the outcome of A has no possibility of occurring at the same time as B, then it's called mutually exclusive. And remember, I think there was a question that we did together where there was like, is it possible to vote? Remember, it was like, is it possible to play mute the instrument and have the instrument be a clarinet? Yes. Is it possible for a person to have blonde hair and blue eyes? Yes. Is it possible to vote Democrat and Republican at the exact same time in the election booth? No. So that was mutually exclusive. That was that one. So here again, probability of rolling a 6 on a die or rolling a 3. You can't roll a 3 and 6 at the exact same time. So that's mutually exclusive. This is really important. It's like one of those core concepts in probability, this idea of mutually exclusive. I would expect at least one mutually exclusive question on your EOC. If the outcome of A can occur at the same time, then we use this formula. Okay. So for example, the probability of rolling greater than 3 or an even number. Well, there are numbers greater than 3, 4, 5, and 6. 4, 5, and 6, 4 and 6 of them are even. So that means that we use that special formula. Okay. If you can't get both, that's this. If there's some kind of overlap, that's where we're going to go into that formula. Okay. Here's the formula. Conditional probability is the probability of A given that B happened. So B is essentially, in this case, the first thing that happened. Even though B comes after the letter A, that's just how they write this formula. So the probability of A happened given B. The probability of A given B is first, you just do the normal probabilities by multiplying them together, and you divide by the probability of the first thing happening. So for example, the probability of having a lost piece of mail given that it was sent to standard post. Well, we don't even care about express post. So then we just look, okay, here's standard, here's lost. So we do standard and lost, and then we divide by standard. Next. Here's some extra tips. Sample space consists of all the possible outcomes. A sample point is each outcome. I don't know that I've ever seen that word before, frankly. Event, a set of sum of all, and then we did that. Either blah, 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 blah. I don't want to keep doing that. Here, we didn't really focus a whole lot on this terminology. I don't recall ever seeing but not. And then subset in is contained in. I don't know. I don't remember seeing it in the EOC questions, but that is there for your ideas. Okay, this is what the state of Georgia says you need to know. So I'm telling you, if there is something on this paper that you should know, this is what it is. Georgia did this paper. All I did was copy and paste it. Sample space we already talked about. Independent we talked about. Dependent we talked about. Okay. Intersection is the and the upside down, the horseshoe. Union is the or, and it's everything. We take the sum. Complement is that not happening. The conditional probabilities, here's A given B, means that B happens first, then we figure out A. And then it says the probability of two events, if they're independent, we just multiply. And then then it just goes on. Two-way frequency tables, I didn't talk to you about yet on here. Okay. And then here I have always put the little rule. So let's go to our first question. Told you we're going to be beast on this. Beast. Okay. Let me get my notebook out because that way I won't mess you up when it's late at night. Which, let's be realistic, I'm known to do. Okay. If V represents a set of all license plates beginning with a vowel. Oh, we did this literally the same question. Okay. If V is vowel, so we have V is vowel. And it begins with a vowel. Okay, and then it says an O represents a set of all license plates that end with an odd number. So we've got 1, 2, 3, 4, 5, and this is odd, and this is vowel. What license plate belongs to the set of, hey, Dariel, V and not O. So we want V to be happy. We want it to start with a vowel, but we do not want it to be an odd number because it says not O. So if it starts with a vowel, we can cross away this because this is not a vowel. Okay. And we want it to not be odd. So in essence, we need it to be even. So the only one that has a vowel to start, which makes us happy and is not an odd number, is choice A. A is for apple. Okay, we're moving on. Trash. Okay, here's the next one. Which of the probabilities would make A and B independent? Well, this is when we're going to look at these independent rules down here. Okay, our independent rules are right here. Okay, formula. If they give you a bunch of stuff like this, go right to the formula. Hey, sweetie, don't we have a calculator somewhere? Do you remember where we put it? Do you mind grabbing it for me? Oh, it's right there. Never mind, I see it. I've got my awesome helper, of course. Thank you, sir. You're going to do it? Freddie's going to help us out. Okay, so in order for it to be independent, when we multiply A and we times B, we should get this number right here. So we're going to do 0.25 times 0.25. This one I think is 0.625. What do we get? Oh, it didn't do anything. This one is definitely 0.625. 0.625. So because... Oh, we're going to do this to hit on to start again. Okay, can you do 0.08 times 0.4? So because we're trying to, if we multiply these together, we got 0.625. We're trying to get 0.5. So because these numbers are different, it's not choice A.
0.032.
He says 0.032 for our next one. Yep, that's right. This says 0.12. So that's not correct because it's not going to be this one. You all done? Thanks for your help, sir. Okay, now this next one, we're going to do 0.16 times 0.24. That's going to give us 0. Hey, Bryson, 0.3. Oh, and Aaron. Awesome. 0.384. That's not 0.32 either. So we're going to take that out. So hopefully it's the last one. Let's do the last one. 0.3 times I hit minus 0.3 times 0.15. And look what we get. Let's see. 0.045, which is the one that we're looking for. So whenever you see a bunch of, I almost said crap, but a bunch of numbers, a bunch of statistics, what I need you to do is go to the formula sheet. Okay. When you go to the formula sheet, you're going to look for the one, say independent events. See how this says independent events? All you're going to do is multiply the two numbers together. If when you multiply the two numbers together, you get this information right here, then you did the problem right. If you don't get it, if it doesn't match, like it didn't match for A, B, and C, then that problem is wrong. Gucci? Cool. Okay, next one. The probability that a high school senior will go to college, assume the following events are independent. Okay, what's the probability that a high school senior will live on campus given that the person will go to college? So we're going to look down here, okay? And the probability of the senior going to college is 0.32. And the probability that a high school senior will go to college and live on campus is that. So this is really simple because look at what they did for you. They gave you literally the only two numbers that you need. You need to know the word and here's the other one. So all you have to know is which way to divide it. Okay, so in this case, the and always goes on top. So 0.46 goes on top. We're going to divide that by 0.72. Let's see. And we get 0.638, which rounded would give you 0.64. Again, they literally gave you the probabilities. Dude, all you had to do was to know to go to the formula sheet. Here's 2 questions in a row that use the formula sheet. That's it. Okay, two-way frequency tables. I kind of jumped quickly through them. Let's take a look. A random survey was conducted about gender and hair color. This table records the data. What is the probability that a randomly selected person has blonde hair, given that the person is a male? Hold on 1 second to make sure I do this correctly. Okay, so this person has to be a male. So the only thing that we care about are males because it has to be a male. See how it says given a male? Given a male, that's the only thing we talk about. So here I'm highlighting males. Everything else does not matter. Boom, da-doom. We don't care about that because it says given a male. So those are the only numbers we talk about, meaning specifically that our numerator is going to be blonde and our denominator is going to be males. So how many blonde males do we have? Ooh, wait, is it blonde or brown? What did I just do? Yeah, blonde. So we have 876 blondes who are males, and we have 1,506 males. And then when we do that division, we get 0.581, which gives us, choice C. Okay, so again, this is the main one. Hey, Lexi. I like your emoji. This is the main one where whenever it says given, we literally don't care about anything else because the other stuff never even happened. All we care about in this case is males. If it said given females, then we'd cross everything out except females and then look at that information. If it said just plain old blonde, ooh, are you okay? If it said just plain old blonde, then that's something different. Oh, sugar shoots, my laptop fell. Okay. So going on, everything's okay. You're okay. Go on. You can go up. Hey, let me move this out. There you go. Go lay down. Of course, it wouldn't be a video unless Ginger was somehow in it, right? So, okay. Now we're going to look at this next one. A random survey was conducted to gather information about age and employment. I think this is in the front of my book. What is the probability that a randomly selected person surveyed has a job given that the person is less than 6 or less than 18? Let me find my notes. notes. Okay, here we go. Given that the person has a job. So first things first, we know that we're going to have to look at the total number of people surveyed that's less than 18 years old. So we're going to go here and look at the table already gave it to us. So here it is. Boom, color. So this is what we need. These people are less than 18 years old. So now it's going to say, given what's probability the random six persons has a job less than 18. So here's has a job. Here's less than 18. 20 divided by 265. And that's going to give us 0.75. Oh, 0.075. So here we would pretty much round it to 0.8. What is the probability that a randomly selected person surveyed has a job given that the person is greater than or equal to 18? So now this is going to be our new number, 679. And then we have our has a job. So we're going to do our 587 divided by 679. That's going to give us our 0.864. So 0.86 is sufficient. Are having a job A and being greater than B independent events, yes or not? No. So in order for us to do that, it says probability A has a job, does not have a job. The best thing that we can do is figure it out using this conditional probability formula. Okay. So what we're going to do is first do the probability of A and B. And then we're going to divide by the probability of B happening. So it says that are having a job. So that's our A event. So I'm going to take this. Let's erase this. Okay. Actually, you know what? Let me just erase all this stuff so that we don't get confused. Okay. So having a job, A. So first we're going to find the probability of having a job and being 18 or greater. So we have 587 has a job, pen tool, Michelle, and our total. So that's going to give us 587 divided by 944. Okay. So then we're going to look at what's the probability, and how we got that again is here's has a job this way, here's 18 and greater, and where they intersect was 587, and there's 944 people altogether. I'm sorry, I should have clarified that. In the back of my head, I'm listening for Freddie's dad to come. The next thing is what's the probability of B happening? What's the probability of it being 18 or greater? 18 or greater. See, there he is. 18 or greater is 679. Okay. And then I'm going to, guys, I'll be right back. Hold on. I'm so sorry. Okay. Click this, click this, click this. Be right back. Come on, let's go, baby. Hey, run away. Hi guys, sorry about that. Okay. Yay. Okay, Freddie is now gone. Here we go. So now I can give you better attention. And I'm going to start the problem over one more time. Okay. We're still looking down here at C. In order for us to figure out the conditional probability, we need to see where they match up. So how this is the probability of A and B happening, because it says having a job, hey Cam, and greater and being 18, we're going to look where does has a job and where does 18 or greater match up. See how they match up at 587? So that's going to be my numerator, 587. Now I'm looking for how many people are there all together? 944. So then using my calculator, I will do 587 divided by 944. And this is going to give me 0.62. And this number is just my numerator for that formula from the formula sheet. Then I need to figure out, okay, what's the probability of someone being B? And B is 18 or greater. So then I'm like, well, the 18 or greater, there's 679 people who are 18 or greater. And there's 944 total people. So then again, I'm just going to do 679 divided by 944. And that's going to give me 0.72. So that gave me my bottom one down here. Now all I do is the division. 0.62 divided by 0.72, and I get 0.86. Hold on. Hold on. That is actually... I was just doing it wrong. Hold on. I'm sorry. That's what it is for B. I was getting my notes messed up. So that's how we do it for B. Okay. Now it says the events are independent. So that's B's answer. The events are independent. And that's B's answer because of the word given. And I wasn't paying attention when I was paying attention with Freddie. So I apologize. So all of that hard work was for B. Now for C, the events are independent. So we're going to look at our 0.86. Okay. And that's how we got here. We got our 0.86. And then if we look at, are having a job and being 18 or greater independent events? So if we look at having a job, that's 607, pen tool, and we divide it by 944. Okay, because we're looking at having a job and 18 or older. So we're just figuring out what's the plain straight probability of having a job. Because if having a job and being 18 or older, if those numbers become the same, then we can say that we can determine their dependence from there. So we're going to do 607 divided by 944, and that's going to give us 0.64. So now we're going to compare. See how this is 0.64 and the one that we just said 0.86? Because these two numbers do not equal each other, then they are not independent. So in essence, it does matter. Your age does depend on, having a job does depend on your age. So here, this is where I screwed up before. I didn't talk about the given piece. So that's what all that work was for there. And then the final piece is we compare them back and forth. Guess what? You will not have a problem that detailed on your EOC. Okay, next question. In a certain town, the probability that a person plays sports is 65%. The probability that a person is between the ages of 12 and 18 is 40%. The probability that a person plays sports and is between the ages of 12 and 18 is 25%. Are they independent? How do you know? Well, first of all, let's just say P of S. Yep, the next test is all multiple choice for probability. So the probability of S is that they play sports. And we're going to have the probability of A for age, represent them being between 12 and 18. Okay. If the two events are independent, then we know we can use that formula down here, that the probability of S and B will equal the probability of S times the probability of B. So now we're pretty much going to fill in information. So in a certain town, the probability that a person plays sports is 6.65 is 65%. So we can put 0.65. The probability that a person is between the ages of 12 and 18 is 0.4. The probability that the person plays sports and is there is this. So we're checking it. All we're going to do, as long and complex as that is just multiply these numbers together. If these numbers equal 0.25, then yes, we can say they're independent. If they don't, then we can say they're not independent. So we actually get 0.26. And that 100th makes a difference. 0.26 does not equal 0.25. So the events are not independent. It's literally that simple. Okay. This is a question I would expect that you're going to end up seeing because, again, it's one of those core concepts in geometry. So all we did is we just made up our little numbers, or we came up with our plan of this P of S equals this, playing sports, P of A equals this. We've got the probabilities from reading the problem. We multiplied them together and we compared it to the original. Because it didn't, I mean, if it said 0.59, you could round to 0.26. But like that, we don't round. It just stays just like that. Okay. So here we go. Mutually exclusive events. If two events are mutually exclusive, they cannot happen at the same time. When two events A and B are mutually exclusive, the probability of A and B happening is the sum. If they're not mutually exclusive, then there's a longer formula. Again, that's on the formula sheet. And you can find conditional probabilities. And there was an example that I copied over for you from the book. Let's go over some examples. In Mr. Mabry's class, there were 12 boys and 16 girls. On Monday, 4 boys and 5 girls were wearing white shirts. If a student is chosen at random from Mr. Mabry's class, what is the probability of choosing a boy or a student wearing a white shirt? Well, okay, the first thing is we're going to look at the addition rule. And here's our addition rule right here. Okay, again, this is on the formula sheet. Okay, and it says that, let's write the addition rule. Why am I doing this? Okay, so basically what we're going to do is A is boys, and we'll have B be the white shirt. Okay, and let's see, A and B is the set of boys wearing a white shirt. So let's look. First of all, how many students are there in class? So we're going to do 12 plus 16, and this is going to give us our total number of students. So the probability that we have a boy is 12. Okay. Then we want to see what's the probability that a person wore a white shirt. So we're going to add these numbers up. 4 plus 5, we had 9 people wearing white shirts. But if you're a boy and you wore the white shirt, there's some double up. So 4 boys wore both. So we're going to subtract them out. When we do the math, we get 17. And that's it. Okay. It looks complex, but again, it's really seeing, is there a formula that can help me out? If you see the word given, you're going to use that conditional probability more often than not. Okay. If it says something like and or the double up, that's where that addition rule comes into play. The next one, we're going to use additional rule again. It says if a student is chosen at random, what is the probability of choosing a girl or a student not wearing a white shirt? So now we're going to still have our P, A or B, equals the probability of A, but this time the probability of A is going to be a girl. And I did not intend to use blue and pink. I'm sorry if that impacts anyone. And the probability of B, which in this case is no white shirt. Okay. That's a shirt. Probability of A happening a girl. Well, there's 16 girls. So we're going to do 16 over 28. Still the same number of kids. Oh, and then we have to subtract the probability of A and B. Then how many people are not wearing white shirts? Well, if 9 students are wearing white shirts, 28 minus 9, 17. Nope, 19. So we're going to add 19 plus 28. Now I'm going to double check myself. 28 minus 9. Syntax error. Plus 0. 19. Okay, we're good. Then we're going to subtract how many students, how many girls did not wear white shirts. Well, here we know there's 16 girls altogether. 5 of them wore white shirts. So 11 of them did not wear white shirts. So again, this is girls. This is did no white shirt, NOW. This is girls with no white shirt. Okay. Then I'm not going to try to do that in my head. 16 plus 19 minus 11, 24. So then we get 24 out of 28, which of course this can be reduced by 4. So we have 6/7. And that's it. Almost done, friends. Terry has a number cube with sides labeled 1 through 6. He rolls the number cube twice. What is the probability that the sum of the two rolls is a prime number, given that at least one of the rolls is a 3? So, okay, this is an example of a mutually exclusive event. So first of all, we're going to come up with all the possible combinations where at least one of the rolls is a 3. So let's go what we can do. Well, first of all, we agree that it could be a 1 and then a 3, a 2 and a 3. You can't have I guess you could have a 3 and a 3, a 4 and a 3, a 5 and a 3, and a 6 and a 3. Okay. So that means the first number was any one of those numbers and the second number was the 3. Or it could be the first number was a 3, second number was a 1. First number was a 3, the second number was a 2. We won't do 3, 3 because we already had 3, 3 counted there. So then we can have a 3 and a 4, a 3 and a 5, and a 3 and a 6. So altogether, there are 11 possibilities. Okay. So basically, we did like a sample space. Then we're going to identify the pairs that have a prime sum. Okay. Because it says, what is the probability that the sum of the two rolls is a prime number? So we know that our prime numbers are 1, 3, 5, 7. What else? Well, 1 is not prime or composite. 9, which is not a prime number. 11 is a prime number. Okay. So then we're going to say, well, you could have, let's see, 1 and 3 is 4. 2 and 3 is 5. That's prime number. That's 6, 7, 8, 9, 4, 5, 7, 8, 9. So how many things did we circle? We circled 4. So our probability is 4 out of 11. Okay. Because it says given that at least one of the rolls is a 3, that's why we use 11 as our denominator, because there's 11 possible combinations. Then the reason why I wrote it out is for me, it was a way easier to cross things out. First, I wrote out all the possible combinations. Then I added the numbers up, saw which numbers were primed, and that's how we were able to do that problem. Okay. Here it says, what is the probability that sum of the two rolls is a prime number, or at least one of the rolls is a 3? So because it said given, that caused it to be mutually exclusive. Okay. Because it had to have a 3 on the first roll. Here, it didn't have to have a 3 on the first roll, or not a 3 on the first roll, but it had to have at least a 3. So now we know that there's 36 possible outcomes when rolling a dice twice. Now we're going to list all the outcomes that have at least one of the rolls is a 3. So we have that. Okay. And then we're going to list all of them that have the prime sum. And that means even if it's not a 3. So we know we have these 11 probabilities. Now we're going to list anything with a prime sum. And I just have to write it out. 1 and 1. This is tedious, but this is literally how I would do this if I were you. 2, 2, 2, 2, 2, 2. 1, 2, 3, 4, 5, 6. 3, 3, 3, 3, 3, 3. 1, 2, 3, 4, 5, 6. I'm literally writing all 36 possibilities. Okay. Okay. So now we have to cross out things that don't make sense. So that's 2. 1 plus 2 is 3. So that works. That's 4. 1 plus 4 is 5. 6. 1 plus 6 is 7. 2 plus 1 is 3. 4. We can, cross out every other one. 7 and 5. 3 plus 1 is 4, so I can cross out every other one because those are going to be even. This is 5. 3 and 4 is 7. 3 and 6 is 9. 4 and 1 is 5. 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. 7. Oh, look at the, I should have just noticed the line to begin with. 9, 10, 11, 12. Okay, so those are all the possible combinations that have a prime sum. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think I'm missing one because they're supposed to be 15. What one am I missing? 1, 1. Oh, yeah, 2. 2 is a prime number. How could I have missed that one? 2 is a prime number because 1 and 2 are neither prime nor composite. Okay, so now we have 15 combinations here. So we have the probability of at least one roll would be 11 out of 36, that we have 1 as a 3, and we have 15 out of 36 is the probability that we would get a prime sum. So now we're going to see, are there any combinations that are overlapped? So here we know that these 4 are overlapped, right? Because we had that from before. Now all we're going to do is take these numbers, add these 2 numbers up, and subtract this number. So you have 11 over 36 minus 15 over 30, plus 15 over 36 minus those overlap. And when you do that math, you're going to get 22 over 36, which reduces to 11 over 18. Yes, this is one you're going to have to watch again. I'm sorry. I put all the longer ones at the end. Okay, next. Thankfully, this is going to go quicker. Hopefully, Mrs. Klein surveyed. Oh, I didn't copy and paste everything over. That's unhelpful because C was 74 over 105. And D was 88 over 105. Okay. Mrs. Klein surveyed 240 men and 285 women about their vehicles. Of those surveyed, 155 men and 70 said they own a red vehicle. That's a lot of red cars. The person is chosen at random from those surveyed. What is the probability of choosing a woman or a person who does not own a red vehicle? So we're going to do the addition rule again. The probability of a woman is 285 out of the total number of people. 5 to 525. We're going to probably a woman or a person who does not own. So the probability of not having a red complement, and that's any person. So we have to do the math for that. If there's 525 people altogether, 155 plus 70. So we know that 225 own a red car. That means 300 have no red car. So we're going to have adding 300 over 525. And then we have to subtract the number of women who do not have a red car. So that's going to be 215 divided by 525. Okay, so then we just add them up. 285 plus 300 minus 215 gives you 370 over 525. All right, here's my hack. So who wants to reduce all that? Not me. So I'm going to take 525. And I notice that 3 of the denominators end in 105. So I'm going to divide by 105. And know that in order to get from here to here, I had to divide by 5. Now I just do 370 divided by 5, and I get 74. So it's choice C. The other thing you could have done is you could have done 370 and got a decimal. Divided by 525, which gives us 0.70. So then if I do 14 divided by 57, that gives me 0.24. 71 divided by 105 gave me 0.67. 74 divided by 105 gave me 0.7. So that's the other way you could have done that, like the end part. Bianca spins 2 spinners. They have 4 equal sections, numbered 1 through 4. I'm just going to draw the spinners. You remembered when you were married. That's good, Jahir. I don't remember when I was married. Bianca spins 2 spinners that have 4 equal sections, numbered 1 through 4. If she spins a 4 on at least one spin, What is the probability that the sum of her 2 spins is an odd number? Okay, well, she needs to get a 4 on 1 spin. So here she has a 1 in 4 chance. And here she has a 1 in 4 chance. Okay. And then it says the sum is an odd number. I don't feel like writing combinations out. Basically, you have to write combinations out. Let's see how many. This is our last problem. All right, we could have a 1, 1, 1, 2. Hold on. 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. 1, 2, 3, 4. Okay, so what is probably that the sum of her 2 spins is an odd number? So let me erase this and we'll do it the right way. So if she spins a 4 on at least 1 spin, so that means that we're going to not pay attention. I'm going to erase. No, I shouldn't erase. Let's pen tool. Of course, I did that when I rush. 1, 1, 1, 1. 2, 2, 2, 2. Okay, so we can cross out these because she didn't spin a 4. Okay, then we have those left. What is the and then it says, and at least 1 spin, the sum of her 2 spins is an odd number. So we have 5, 7, 7, 5. So we have 1, 2, 3, 4 possible out of how many total spins that she could have? 1, 2, 3, 4, 5, 6, 7. 4 out of 7. There you go. Again, I know it's tedious, but if you write it out, you do get the correct answer. Okay, each letter of the alphabet is written on separate cards in red ink. The cards are placed into a container. Each card, placed each letter of the alphabet is also written on separate cards in black ink. The cards are placed in the same container. What is the probability that a card randomly selected from the container has a letter written in black ink or a letter, or the letter is an A or a Z? Okay. I hope we can agree. This is an addition rule. Hold on. This is going to be the probability of A and B. This is the addition rule right here. That equals the probability of A plus the probability of B minus the probability of it being both. Okay. So, and this should be or. I was rushing, or. So the probability of that happening, and we're doing it or because it says or right here. Probability of A, what's the probability of getting black ink? Well, it says that each letter is written on black and red. So we know that the probability of getting black is 1/2. Then it says, what's the probability of getting A or Z? Well, we have a red A and a red Z, and we have a black A and a black Z. So that's going to be 4 out of 52 because there's 26 letters in the alphabet. 26 times 2 is 52. Then we're going to subtract how many of them are black and A or Z. 2. And really, to make things easier, I should have made that 26 out of 52. So this is going to give us 28 out of 52. And then we have to reduce. I'm just going to do it the decimal way. 28 divided by 52 is 0.538. So let's look. This is going to be 0.5. 7 divided by 13 is 0.538. So this is our answer. Yeah. Okay. Trash can. Woo! I thought this was going to be a short one. It still took us 50 minutes. Well, I did run away for a couple minutes. So, loves, that is it for tonight. Tomorrow in the comments, 2:30 to 4:45. If you stay the whole time, I will give you 10 bonus points on a quiz grade. I am arranging for pizza to be there. I'm hoping that Domino's will deliver and still give me the in-sale price. Cross our fingers. There is no after school on Tuesday because both Monday night and Tuesday night are going to be the longer sessions where I review the high high level topics across everything. All right, that is it for now. Thank you all for watching and your time. Have a good night. I will see you tomorrow. Ciao. Ciao, 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 ciao.